Welcome back. In the last lecture, we introduced this idea of a hypothesis test. And let me point out that in the last lecture, all the examples involve one sample. Right, we took one sample and then we asked ourselves the question, was there enough evidence to conclude that the proportion or the mean was less than, greater than, or not equal to a fixed number that was given to you in this situation? So those are called one sample hypothesis tests. And these were the two formulas that we use. The first one with the Z was for proportions, which now I'm going to call one proportion. The second one with a T was for means, which I'm going to call one mean now. And those are formulas that we use for one sample hypothesis tests. Today we're going to talk about hypothesis tests that involve two samples. So these are situations like example 1. So let's jump over to example 1. In this situation, we have a drug company that has a new medicine and they want to test out their medicine and see if it works. So typically what happens is they'll take two groups or two samples. One group they'll give the medicine to, and then the other group they'll give a placebo or a fake medicine to. And then they'll ask the question, are these two groups different? In other words, did the medicine do anything? Right? That's a typical two sample hypothesis test. So jumping back to the front page, the second Z formula with the P1 hat and the P2 hat, that's going to be for two proportions. The second T formula with the X1 bar and X2 bar are going to be for two means. And then the box at the bottom, same as last time, these are your commands in R. P norm, Q norm are going to be for your Z situations. PT, QT are going to be for your T situations. On the second page are types of error. Let me skip this for now and come back to this when we actually encounter them. And let's jump to example 1. Example 1. A drug company develops a new medicine. To test out their medicine, a sample of 2,529 people are divided into two groups, a control group and a treatment group. The 1,304 people in the control group were given a placebo, that's a fake medicine, and the 1,225 people in the treatment group were given the actual medicine. 150 people in the control group got sick, and 113 people in the treatment group got sick. Can a company conclude that the proportion who got sick differs between the control group and the treatment group? Use the alpha equals 0.07 level of significance. So this is definitely going to be a two sample hypothesis test, right? We have two groups, the control group and a treatment group. Question is this a proportion or is this a mean question? Can a company conclude that the proportion? So this is definitely a proportion. And in fact, it's going to be a two proportions. And then to remind myself for proportions, I should be using Z throughout the problem. Part A. The null and alternative hypotheses, these are my H0, H1. Because I'm talking about proportions, I should be using P's. And because I'm talking about two proportions, there should be a P1 and a P2. Okay, what's the symbol that goes in the middle? Is it less than, greater than, or not equals? So it says, can a company conclude that the proportion who got sick differs? So differs is going to be not equals. H0 should be exactly the same, except with an equals in the middle. And then because we're talking about two samples here, let me label what one means and what two means. So I have two groups, a control group and a treatment group. It doesn't matter which one is your ones and which one is your twos. Let me just go with the order of the problem. So it introduced control first and then treatment next. So let's let 1 be my control, and then 2 is my treatment. So that's going to help me later on in part C. Part B, find a critical value and sketch the rejection region. So we'll draw our picture. This is either going to be shade to left, shade to right, or two tails. Not equals is always going to be two tails. And the shaded area is our level of significance, our alpha. So the left and right together is alpha equals 0.07. And then we're either finding the z stars or the t stars. This is a proportion question. I should be finding z stars. This is really just an area to z problem. For an area to z problem, area to z, for the z situation, we should be doing q norm. Okay, so we'll q norm the left area. Left and right together is 0.07. If I just want the left, divided by 2. So 0.07 divided by 2. .035. Okay, that's the left area that I'm going to feed R. So we're going to Q norm 0.035. Negative 1.812. Okay, that's a Z star. Based on the picture, I do expect 2 Z stars. The negative 1.812 is the one on the left. The one on the right is going to be positive 1.812. Okay, those are my 2 Z stars. Part C, find the Z or T test statistic. We're talking about proportions. I should be finding Z. And because I'm talking about 2 proportions, I should be using a second Z formula, which is this one. This formula has a P1 hat, a P2 hat, a P hat with no number, N1 and N2. So let me write all those down. So I need a P1 hat, a P2 hat, a regular P hat, an N1 and an N2. P1 hat is going to be the proportion from my first sample, so which is the control group. So for my control group, how many people total and how many people got sick? For the control group, there's 1,304 people in the control group and 150 people in the control group got sick. So P1 hat is going to be 150 out of 1,304. Okay, so 150 out of 1,304, 0.115. P2 hat is the proportion for my second group, which is the treatment group. So how many total in the treatment group and how many people got sick? 1,225 people in the treatment group and 113 people in the treatment group got sick. So it's going to be 113 out of 1,225. So 113 out of 1,225, 0.092. So round these to 3 decimal places. And then we have a regular P hat with no numbers. So go back to the front page. P hat with no number is the pooled proportion, and it's telling you x1 plus x2 over n1 plus n2. This is basically telling you to take your 2 top numbers of your P1 and P2, which is 150 and 113, add them up, and that's going to be the top of the P1 or the P hat. And then take the 2 bottom numbers, add them up, and that's going to be the bottom. P1 hat is going to be 150 plus 113. And then on the bottom, 1,304 plus 1,225. And so what are we actually calculating here? So the bottom is we're just taking both groups and adding up together, the total for both groups and adding up together. So that the bottom is just the total of everybody, both groups combined. On top, we're adding up the top numbers of the 2 fractions. So these are the people who got sick in both groups. And so we're just combining those together also. So this p hat with no number is just a proportion of everybody, both groups combined, who got sick. All right, so in Desmos, up top, 150 plus 113. On the bottom, 1304 plus 1225. 0.104. That's rounded to 3 decimal places. And 1 is the total number of people, sample size for our first group, which is the control group. That should be the bottom of the first fraction. That's 1304. And 2, sample size for the second group, the treatment group. That should be the bottom of the second fraction. That's 1225. All right, so we have everything we need to plug into the Z formula. So I'm going to type this in directly into Desmos. If you're not using Desmos, why not? I highly recommend you use Desmos for these problems because the formulas are pretty complicated here. And in Desmos, I can just type it in directly like that. So in Desmos fraction, up top, it's P1 hat minus P2 hat, which is going to be 0.115 minus 0.092. So up top, 0.115 minus 0.092. On the bottom, square root. So square root P hat, and in parentheses, 1 minus P hat. So P hat is 0.104, okay, 0.104, parentheses, 1 minus 0.104, close parentheses. Okay, open another parentheses, and it's going to be a fraction, 1 over n1, and that's going to be 1 over 1304, plus another fraction, 1 over n2, so 1 over 1225. And then we'll close the parentheses. Okay, make sure what you see on Desmos looks exactly like this. In particular, make sure that the square root, the line above the square root, goes across the entire P hat, 1 minus P hat, 1 over n1, 1 over n2. Okay, once you make sure that it looks exactly the same, I'll hit enter. And we get a Z of 1.894. And that's our test statistic. Part D, find a p-value, draw the picture. The picture should be the same as whatever you drew in part B. Because it's not equals, it's going to be 2 tails. We're going to put our test statistic on the picture that we found in part C. 1.984 is the one on the right. 1.894, which means the one on the left is going to be negative 1.894. And your job here is to find the shaded area. That's the p-value. That's the p-value. This is really just a Z to area problem. So Z to area. Z to area for the Z situation is a p-norm. So we're going to p-norm something. What do you p-norm? Do you p-norm the positive 1.894 or do you p-norm the negative 1.894? So just like last time, p-norm always gives you the area to the left of whatever you plug into it. I'm not going to plug in the positive Z because the positive Z is going to give me the area to the left, which includes this unshaded part, which I don't want. So I'm going to plug in the negative because I do want what's left of the negative 1.894. So we're going to plug in a negative. So p-norm negative 1.894, 0.029. Okay, 0.029 is the area to the left of negative 1.894. So that's this part. And I want the area of both shaded sections together. All right, so if the left one is 0.029, the one on the right by symmetry is also 0.029. And then either add those two things up or take one of them and multiply them by 2. So I'm going to multiply by 2. Right, so 2 times 0.029, 0.058. Okay, so let's talk about what this p-value means in this situation. So the p-value is saying, okay, so we're trying to decide whether the two proportions are actually different, right? The P1, the control group, had a proportion of 0.115. The proportion for the second group, the treatment, is 0.092. So yes, they are different, but the question is, are they different enough to matter? So the question is, could these two differences have happened just by pure chance because we have two different groups of people? So what this p-value is saying is, assuming H0 is true, so assuming that the two groups are actually the same, this difference that we're seeing could have happened by pure chance this percent of the time, which is 5.8%. Okay, so this is the probability of this difference that we're seeing happening by pure chance, assuming that H0 is true. And it's a pretty small number, right? So which means it's pretty rare to happen by pure chance. And it's small enough, it's so rare, that we're going to say that it probably did not happen by chance. That it couldn't. A better explanation is that it did not happen by chance, and in fact, that H0 is false. And the criteria, what's considered so rare that we're going to say H0 is false, is going to have to do with the alpha, the significance level. So for part E, we're going to check our p-value and see if it's less than our bar alpha. Our p-value is 0.058. Our alpha is 0.07. If it's less than, we reject. If it's not less than, we don't reject. 0.58 versus 0.7. So if you can't tell, add zeros to match the number of decimal places. This one has 3, 0.70. So it is less, right? This is really just 58 versus 70. So 58 is less than 70. It is less, so we are going to reject. And then our settings. At state your significance level, so at alpha equals, we said was 0.07. Level of significance, there is or is not. So if you reject, there is enough evidence. If you did not reject, there is not. So in this case, we did reject, so there is enough evidence to conclude, and then state H1 as a sentence. So H1 basically is saying that the proportion for the control is different than the proportion for the treatment. But I'm actually going to go up to the question and write it that way. So can the company conclude that the proportion who got sick differs between the control group and the treatment group? So the proportion who got sick differs between the control group and the treatment group. And that's basically a hypothesis test that we talked about last time. So for this section, I'm going to add one more question, which is what type of error could have occurred, and what is the probability of this error occurring? So anytime we're doing a hypothesis test, right, we're making our decision based on the data, right, based on the sample that we're taking, and that tells us whether we're going to reject or don't reject. So because we're basing our decision on the data, on the sample, there is a chance that the sample is telling us to do something that's not correct, right? So in this situation, the data could be telling us to reject H0 when in fact H0 could in reality be true, which means that we're making a mistake by rejecting it. So that's called a type 1 error. So let's talk about what a type 1 error is. A type 1 error occurs when we reject H0 when in reality H0 was true. So we made a mistake, right? We rejected H0 when in reality H0 was true. And in other words, the data, the sample is telling us to reject when in reality H0 is true. So what's the probability of this happening? The probability of a type 1 error is actually the alpha, the significance level. Okay? So, and obviously, we usually don't want to make a mistake, right? So what's the how do we reduce the probability of a type 1 error? Well, the probability of a type 1 error is alpha, so if I want to reduce the probability of a type 1 error, just lower your alpha. So we're going to lower, you can reduce the probability of a type 1 error by lowering the alpha. So to answer the question here in part G, what type of error could have occurred? So anytime you are rejecting H0, you could be making a type 1 error, right, which occurs when you reject H0. To answer part G, we could be making a type 1 error. And the probability of a type 1 error is the alpha. In our case here, it's 0.07. So to lower the probability of type 1 error, we could lower the alpha, but then this means we have a trade-off, right? If I lower the alpha, for example, if I lower the alpha to say 0.05, what happens? If I lower the alpha, notice that if I lower it to 0.05, this will no longer be a reject, right? Because then 0.058 would no longer be less than 0.05. So if you lower the alpha, yes, you lower the probability of an error, type 1 error, but you also make it harder to get a reject. And the reality is you want to reject, right? If you're doing a research project, if you're this company, the way you get your paper published or the way you get this medicine to show that this medicine worked is to get a reject. So that's the trade-off. You can lower the alpha, and that's going to lower the probability of this type 1 mistake, but it also makes it harder for you to reject, which is what's going to make you the money, right? It's what's going to get you published. It's what's going to get you in the newspaper. It's what's going to show that this medicine works. All right, type 2 error. Let me skip this for now and talk about type 2 error when we actually encounter it. Example 2. A simple random sample of 17 business majors from a certain university had a mean GPA of 2.81 with a sample standard deviation of 0.27. A simple random sample of 23 psychology majors was selected from the same university, and their mean GPA was 2.97 with a sample standard deviation of 0.23. Can you conclude that the mean GPA of psychology majors is greater than that of business majors? Use the alpha equals 0.02 level. This is definitely going to be two samples, right? We're talking about two groups here, business majors and psychology majors. And the question is, are we talking about means or are we talking about proportions? can you conclude that the mean, okay, so this is definitely a mean, and in fact it's going to be two means. And then to remind myself, for means, I should be using t's throughout the problem. Part A, state the null and alternative hypotheses. These are my H0, H1. Because I'm talking about means here, I should be using the mean symbol, which is mu. And because I'm talking about two means, there should be mu1, mu2. And the question is, what goes in the middle? Is it less than, is it greater than, or is it not equals? Can you conclude that the mean GPA of psychology majors is greater than that of business majors? Okay, so it does say greater, so I'm going to go with greater. H0 is going to be equals. And then here it's going to be important for you to label what 1 is and what 2 is. So it says, can you conclude that psychology majors is greater than business majors? So I have to put 1 as psychology majors and 2 as business majors. Okay, because I want it to be psychology is greater than business. So 1 has to be psychology majors and 2 has to be business majors. So be careful there. Part B, find the critical value and sketch the rejection region. This is either going to be shaded left, shaded right, or two tails. Because we're doing this as a greater than, this is going to be shaded to the right. I should actually back up here. You could go the other way, right? If you put business first and psychology second, that's fine. But then the sign would actually have to be less than, right? Because psychology greater than business is the same thing as saying business is less than psychology. So you could say 1s are your business and 2 are your psychology, but then you would have to put a less than here, which is fine. Okay, so that's my shade to the right because I'm going with this order. Alpha is the shaded area, so our alpha here is 0.02. Okay, that's the shaded area. And then I'm either finding a Z star or a T star. I'm talking about means here, so I'm looking for a T star. This is basically a area to T problem. So area to T. Area to T, I should be doing, for the T situation, QT left area DF. So we're going to do QT. Left area. 0.02 is not the left area. 0.02 is the shaded area, which is to the right. I want the other side. To get the other side, 1 minus. 1 minus 0.02 is, I believe, 0.98. Yeah. Okay, that's what U feed are. QT has a DF, degrees of freedom, which is 1 less than the sample size. Now, for 2 samples, which sample size do you use? So you actually use the lower sample size. Okay, so we have a sample size of 17 business majors and 23 psychology majors. So we're going to use the lower sample size, which is 17, and the DF is 1 less than the sample size. So 1 less than the 17, which is going to be 16. So once again, you don't combine the sample sizes, you use the lower sample size, and then the degrees of freedom is just 1 less than the lower sample size. We're going to do QT, 0.98, comma 16. 2.235. Okay, this is a T star. I do expect just one answer, so that's my answer. And I did expect an answer on the right side, so I have positive answer. So this looks right. If for some reason you got a negative answer, you probably forgot to do the 1 minus here, which is fine. Just take the negative off and you should be good. So make sure your answer matches your picture. Part C, find a Z or T test statistic. We're talking about means. I'm looking for a T here. And we're talking about 2 means, so I should be using the second T formula, which is this one. This formula has an x1 bar, x2 bar, S1, S2, N1, N2. Let me write all those down. X1 bar, X2 bar, S1, S2, N1, N2. Okay. This is where your labeling becomes important. So X1 bar is the mean for your first group, which is the psychology group. What is the mean for psychology? The mean for psychology is not 2.81, right? That's the mean for the business. The mean for psychology is actually 2.97. So 2.97. X2 bar, that's the mean for my business majors. The mean for business, we said was 2.81. S1, that's the standard deviation for my first group. So standard deviation for psychology majors is psychology standard deviation 0.23. S2, that's the standard deviation for my second group, which is the business majors. So standard deviation for the business majors, business is talking about here, standard deviation 0.27. N1, that's the sample size for my psychology majors. Sample size for psychology is 23 psychology majors. N2, sample size for my business majors. Sample size for business, 17 business majors, 17. And then enter this into the T formula, the second T formula. All right, so in Desmos, fraction up top, X1 bar minus X2 bar, that's going to be 2.97 minus 2.81. On the bottom, square root. Okay, and then we have a fraction inside the square root, so fraction. First one, S1 squared over N1. S1 is 0.23, so 0.23 squared over N1, which is 23, and then plus. So here, move your cursor just to the right of that fraction and hit plus. Right? If you move too far and hit plus, that plus is going to be outside of that square root, which you don't want. You want everything inside the square root. So if you're getting a plus that's outside the square root, just move your cursor just to the right of the fraction without any spaces and then hit plus. And that should put it inside the square root. Okay, and then another fraction. Second fraction, S2 squared, is going to be 0.27 squared. So 0.27 squared over N2, 17. Okay, make sure everything looks exactly like the formula. Okay, once it's good, you can hit enter, and that's our T here. So our T is 1.971. Part D, find a p-value. We're going to draw the same picture that we drew in part B. Greater than, it's going to be shaded to the right. Put your test statistic on the picture. So there's just one here. 1.971. Okay, it should match your picture, right? I do expect a positive to match my picture that's shaded to the right. If you're getting a negative answer here, what probably happened is you mixed up your ones and twos. Okay, which is okay. Just make it positive to make it match the picture. Okay, so this is shaded to the right. I expect this to be positive, so make sure it's positive. And this is really just finding the area. That's our p-value. This is a T to area problem. T to area for the T situation is going to be PT. So PT, T, DF. So we're going to do PT. The T, which is 1.971, comma the DF. We talked about this already. The DF is going to be 16. So we're going to use the lower sample size and then subtract 1. So that's 17 minus 1. Okay, PT 1.971, comma 16. 0.967. Usually p-values should be small. This can't be right. 0.967, 96.7%. That can't be right. And that's because PT and p-norm always spit out the left area here. So this is the left area. And we're not looking for a left area. I'm looking for the right area. So 0.967 is the left area. That's this unshaded part. To get the other side, you need to do a 1 minus. So we're going to do a 1 minus. 1 minus 0.967 is 0.033. Part E, reject or don't reject H0. To decide, we're going to look at the p-value and see if it's less than the alpha. P-value was 0.033. Alpha for this problem was 0.02. Okay, if you can't decide, match up the number of decimal places. This one has 3, this one has 2, so add on the 0. 033 versus 020. That's 33 versus 20. Definitely not less. If it's not less, then this is a don't reject. And I forgot to use the critical value approach in the last example, so let's do it here. The critical value approach, this boundary is 2.235. Question is this t in the shaded part or is it in the unshaded part? 1.971 would be to the left in the unshaded part, right? If it's in the unshaded part, you don't reject. If it's in the shaded part, you reject, because that's called the rejection region. So the critical value approach also tells us to don't reject, so that's a good way to check your answer. Part F, the sentence at alpha equals, it was 0.02. Level of significance, there is or is not, because we did not reject, there is not enough evidence. And then to conclude, and then write out what H1 is, right? So because we didn't reject H0, we can't say that H1 is true. H1 says we're talking about GPA, the GPA of psychology is greater than GPA of business. Or go back to the question, can you conclude that the mean GPA of psychology majors is greater than that of business majors? So mean GPA of psychology majors is greater than that of business. Okay, and now to part G. What type of error could have occurred and what's the probability of this error occurring? Okay, so anytime you don't reject, you could be making what's called a type 2 error. So let's talk about type 2 error. A type 2 error occurs when we don't reject. So when we don't reject H0, when in reality H0 was false. So H0 is false, but the data is telling us to do the wrong thing. It's telling us to not reject H0, even though it's false. Okay. Now, the probability of a type 2 error probability of type 1 error is the alpha, the significance level. The probability of a type 2 error is a number called beta. And we're not going to compute this in this class. It's a little bit more complicated to compute, and we're not going to do it in this class. So I'm going to write, we won't compute this. But I do want you to know that it's a number called beta. Okay, so to answer our question in example 2, what type of error could have occurred, and what's the probability of this error occurring? Okay, anytime you don't reject, you could be making a type 2 error. And then the probability of this occurring for a type 2 error is a number called beta, and you just write down beta. So what's really going on here is the data is telling us to not reject, when possibly, in fact, H0 is false. So why is the data telling us to not reject? What's happening here is that the p-value is not low enough, right? The p-value just happens to be not low enough for us to get a reject. So how do you reduce the probability of a type 2 error? Well, there's a dishonest way to do it. So the dishonest way to reduce a type 2 error is, so if the p-value is not low enough for you to reject, what you could do, the dishonest way to do it, which I'm not going to write down, but the dishonest way to do it is to pick a higher alpha, right? If I had picked an alpha of, instead of 0.02, if I picked a alpha of 0.04, then it would now be a reject. But that's the dishonest way to do it. That's like looking at the answer first and then cooking it up so that you get a reject. So I'm not going to even write that down. The better way to do it is to increase your sample size. So if indeed H0 is false and the p-value is just not low enough for you to get a reject, increase your sample size. So if you increase your sample size, mathematically what's happening is when you increase your sample size, right, because the sample sizes are actually on the bottom, actually in both of these formulas, they're on the bottom. So if you increase your sample size, it makes the bottom smaller, which would make the overall test statistic bigger. And what happens is t becomes bigger, which means t is going to move more to the right. And if you move more to the right, you'll get a smaller area. That's mathematically what's going on. Example 3. The concentration of benzene was measured in 5 random specimens of untreated water produced at a gas field. The mean was 7.8 milligrams per liter with a sample standard deviation of 1.4 milligrams per liter. 7 random specimens of treated wastewater had a mean benzene concentration of 3.2 milligrams per liter with a standard deviation of 1.7 milligrams per liter. It is reasonable to assume that both samples come from populations that are approximately normal. Can you conclude that the mean benzene concentration is less in treated water than in untreated water? Use the alpha equals 0.03 level. Okay, definitely two proportions, right? We're talking about a group of 5 untreated water and then a group of 7 treated water. So two means or two proportions. Can you conclude that the mean? So this is a two mean question. And to remind myself, I should be using t's throughout. H0, H1. Because we're talking about means, I should be using the symbol for mean, which is mu. And because we're talking about 2 of them, it should be mu1, mu2. mu1, mu2. All right, so this says, can you conclude that the mean benzene concentration is less in treated water than in untreated water? So I'm going to go with a less here. And then H0 will be equals. And it's going to be important for us to label what 1 is and what 2 is. For this to be a less, I want it to be less in treated water than in untreated. So I want treated to be less than untreated. So 1s have to be treated and 2s have to be untreated here. You could go the other way, right? You could go untreated and then treated, but then you would have to switch the sign, because treated being less than untreated is the same thing as saying untreated is greater than treated. So you could go untreated greater than treated. Part B, find a critical value and sketch the rejection region. I'll draw my picture. For less than, this is going to be shaded to the left. And we're either finding the shaded area actually is the alpha, which is 0.03. And then we're either finding the Z star or the T star. We're talking about means here. This is going to be a T star. And this is going to be a area to T question. Area to T for T situation is going to be QT, left area df. So we're going to do QT, left area 0.03 is the left shaded area, so we don't have to do anything to it here. So 0.03. QT has a df. So df for 2 samples, you use the lower sample size. Lower sample size would be, we have 5 versus 7, so it's going to be 5. df for 5 is 1 less, so it's going to be 4. All right, so we're going to do QT 0.03, comma 4. Negative 2.601. Okay, and that's a T star. Okay, make sure it matches your picture. This is shaded left. I do expect a T star that's on the left side, so I do expect a negative answer. If you get a positive answer, if you stick a negative, that would probably work. Okay, make sure it matches your picture. Part C, find a Z or T. We're talking about means. I should be finding T's. And we're talking about 2 means. So I should be using the second T formula, the one that has an x1 bar, x2 bar, s1, s2, n1, n2. So x1 bar, x2 bar, s1, s2, n1, n2. All right, so this is going to be important that you labeled it correctly. X1 bar is going to be the mean for treated water. So the mean for treated is what? Treated is talking about treated right here. Treated, the mean is 3.2. X2 bar, that's going to be the mean for untreated water, which is talked about up here. Untreated, the mean is 7.8. S1, standard deviation for treated water. Standard deviation for treated water is 1.7. S2, standard deviation for the untreated water. Untreated water was talked about first. Untreated water, standard deviation is 1.4. N1, sample size for treated. Sample size for treated is 7 specimens of treated, so that's 7. N2, sample size for untreated. Untreated was up front. It was 5. So 5 random specimens of untreated, so it's 5. And then enter this into Desmos, into the second T formula. So we'll start off with a fraction. Up top, x1 bar minus x2 bar. That's going to be 3.2 minus 7.8. On the bottom, square root, fraction. S1 squared over N1. S1 is 1.7, so 1.7 squared over N1, which is 7. Okay, plus, so this is where you want to move your cursor just to the right of that fraction and hit plus. Make sure the plus is under the square root still. And then another fraction. S2 squared, which is 1.4 squared, over N2. N2 is 5. All right, make sure everything looks exactly like the T formula. and then hit enter. Negative 5.127. Okay, that's a T. Part D, find a p-value. The picture should be the same as in part B. This is a less than, should be shaded to the left. And then put your test statistic that you found in part C on a picture. Negative 5.127. Right, so because it's shaded to the left, I did expect a T of that's negative, right? So this does match my picture. If for some reason you had a positive answer here and your picture shaded left, what probably happened was you swapped your 1s and 2s. So chances are if you stick a negative on it, it's probably correct. All right, so this is a T to area problem. That's what p-value means, it's the area. T to area for a T situation is going to be PT, TDF. So we're going to do PT, feed it to T, comma DF. DF is, we're going to use the lower sample size, which is the 5, and then one less than that, which is a 4. All right, PT, negative 5.127, comma 4. Round to 3 decimal places, this is 0.003. And then the question is that the answer, or do you have to do like a 1 minus to it? This always outputs the left area. Question is, are we looking for left area? Yes, we're looking for left area. This is exactly what I want. So 0.003. Part E, reject or don't reject. Look at your P and see if it's less than the alpha. Our p-value is 0.003. Our alpha is 0.03. Is 0.003 less than 0.03? If it's hard for you to tell, match. Make sure that they have the same decimal places. This has 3, this is 030. So this is really a question of whether 3 is less than 30. Yes, it is. So this is a reject. And then you can also use the critical value approach. The boundary here is negative 2.601, and where is negative 5.127? Negative 5.127 would be to the left of that, which would put it in the shaded region, which is the rejection region. So if you're in the rejection region, you should reject, which is telling us to do the same thing. Part F, at alpha equals, it was 0.03. Level of significance, there is or is not enough evidence. If you rejected, then there is enough evidence to conclude that and then rewrite H1 as a sentence. So this is really just saying that the mean for treated water is less than the mean for untreated. Or go back to the question, can you conclude that the mean benzene concentration is less in treated water than in untreated water? So the mean benzene concentration is less in treated water than in untreated water. Part G, what type of error could have occurred? Okay, this is either a type 1 error or a type 2 error. Anytime you reject, you could be making a type 1 error, right? Anytime you don't reject, you could be making a type 2 error. So because we rejected, we could be making a type 1 error. So this is a type 1. And then the probability of a type 1 error, probability of a type 1 error isn't the alpha. So our alpha here is 0.03. All right, so those are all two-sample hypothesis tests. So this lab combines both the two samples together with the one sample. So if you need a refresher on the one sample, take a look at the previous lecture, the one on chapter 9. All right, have a good day. See you guys later.